Okay, welcome to Geospatial Engineering Online Homeschool. Today we will be seeing an exercise. We'll be talking on an exercise on the radial leveling. And the exercise is calculation of height of natural ground and the project height. And this is below. We have the exercise. Let's just read. A radial leveling survey was carried out along a proposed corridor for a road project. Points were established along the axis of the center corridor and site readings were observed with the aid of a dumping level, and the changed distances between the points were recorded. A. Calculate the height of natural ground of each point. B. Calculate the project height of each point. And C. Calculate the working height of each point. D. Draw the longitudinal cross-section and the lateral section of the road with horizontal scale 1:1000 and vertical scale 1:100. Right here we have figure 1, which shows a planimetric view of the corridor. These were the points from BM6, A, B, C, D, right up to H. This is a planimetric view. And they want us to draw the longitudinal section of this road along the center axis of the road. That is from BM6 right up to G. They want us to draw a longitudinal section showing the natural ground and showing the project height. And here is the lateral profile. These are the lateral profile. We see the distance between the initial lateral profile and, let's say, lateral profile number 2. This is what we call the working interval. This is the working interval between the different lateral profile. Then if we look across here, figure 2, we are going to see a cross section. This is just like a cross-sectional view across the longitudinal section of the corridor from BM6 right up to G. We are seeing the point. This is BM6. We are seeing point A, point B, point C, station 1, point D, point E, point F, right up to G. Now, if we look at this sketch here, we are going to see the height of BM6, which is simply the vertical distance from the plane of reference or from the datum to the summit of the point BM6, and the height of point A, which is the vertical distance from the datum to the summit of point A. They want us, and this height of point, height A, BM6, height B, height C, height D, height E, this is what is known as height of natural ground. They want us to calculate the height of natural ground following the observed reading. If we look here, we have ST1, station 1, then we have the first reading here from on the point BM6, 0916. This reading, of course, are always in millimeter. And we have intermediate point SA, SB, SC. And the last reading we take from the station ST1 is a foresight. So we have the first reading backside from ST1 on BM6. Then we have the backside from BM6. Then we have the foresight on point F. Then from point F, now we can now change. We now changed our station and we went to ST2, where we took the backside on point F and the foresight on point G. This method of leveling is known as the radial leveling or leveling by collimation method, whereby we station on a point. We take readings from several points before changing the point. We only change the instrument setup, like from ST1, ST2. We only change the instrument setup whereby when there is no intervisibility between the point and the station point. So we could clearly see that from ST1, it was able for us to take several readings, BM6, A, B, C, D, E, F. And then when there was no intervisibility between this point and the station, maybe because of the topography of the terrain or the distance, that's where we were obliged to change our station ST2 on ST2. It's not like in the case of on the leveling by two staff method, whereby you have to station approximately midway between 2 points and you take your backside foresight, then you change your station backside foresight. But no, this is a radial leveling. Then if we look again, we are going to see something like HPC1, which is the vertical distance from the datum to the line of collimation of the station. So we have HPC1 and HPC2. Then under here we are going to see some, under just beneath you are going to see beneath the section along the corridor, we are going to see pegs, cumulative peg, partial length. These are the partial length distances between the point. Okay, these are the height of natural ground. These are the project height, which we are going to calculate the working height. And this is the gradient of the road. So the road actually have two segments. We have a segment with a gradient of plus 1.00%, and we have another segment with a gradient of minus 0.75%. That is the one to construct the road. Following this segment, there will be under inclination, there will be declination following this segment. Now the first question was to calculate remember the first question was to calculate the height of natural ground. Now before we calculate the height of natural ground, we have to first calculate the HPC. Okay, if we look here, HPC here, we have to first calculate the HPC. The HPC here, if we look here, this distance from here, this distance from the datum to the line of collimation of the instrument is still the same as the height reading of BM6 plus backside. So if we take the height reading of BM6 plus the backside, we are going to have our HPC1. If you look here on the formula, HPC1 equals to height of BM6 plus backside, where HPC is the height of plane of collimation, BS is the backside reading on point BM6, where the reading now, the height of BM6 was given, the height of BM6 was given as 206 meter plus 0.916. Of course, the backside reading were given in millimeters, so we converted it into meter, which is 0.916. We add the two together, we have 206.916 meter. Now HA, now if we look at the sketch, now that we have this reading, we can clearly see from this sketch that if we take all this reading, if we take all the height of plane of collimation minus the side reading, we'll be left with height C. If we take the height of plane of collimation 1 minus the side reading on point B, we'll be left with height B. If we take the height of plane of collimation 1 minus the side reading on point A, we'll be left with height A. That is just logical. So we did all that. We came height A equals to height HPC1 minus side A, where side A is the side reading on point A. So this way the side, when we did that, we had 206.916. The 206.916 was the HPC1 we earlier calculated, minus 0.891. This 0.891 was the side reading on point A that has been converted to meter. So we had an answer of 206.025 meter. So that was the height A. Then we still use the same formula, height B equals to HPC1 minus side B, which is equals to 206.916 minus 0.775 meter. So we use all this method, we use the same method all through. If you look keenly, you're going to see we calculated the height from BM6 from A right up to point G. Then you are going to notice that here we had to calculate a new HPC, which was HPC2, which is equal to height F plus backside reading on point F. Of course, this is HPC. We remember the definition of HPC is the vertical distance from the datum to the line of collimation of the instrument. So, of course, whenever we change our station, we are going to have a new HPC. So this is our new height of plane of collimation 2 on station 2. So we said it will be this height, the height of on point F plus the side reading on point F. So we had, this is it, and we had this, which is 205.354 plus 0.415, which gave us the HPC2. Now we could use HPC2 now to calculate height G, HPC2 minus side G, which is, it gives us this. So we have actually calculated all the height of natural ground from point A right up to point G. Now we are going to move forward now to calculate the project height. Okay. Remember, when we calculate the height of natural ground is simply the reality or what we observe in the terrain. Those are the height that shows the undulating, the rise and fall in the terrain, that is why it is known as height of natural ground. Then we also have a project height. A project height now is, for example, we can go to the terrain and the terrain is rough and they want, and the engineers or the engineers want, or the expert, they want to design, they want to make a design, they want to design a project, a road project, so much so that in a way that a road and the cars can easily use the road. Maybe they want to work on the gradient of the road, like the cut and fill. So they have to design a new height project that they have to work on, other than the height of natural ground. So this is a new height project, and we have been told that initially we have been told that from the first point BM6, we have been told that note the formation height of the initial point of the altimetry project is 0.6 meter. I take it again. The formation height of the initial point of the altimetry project is 0.6 meter lower than the height of the natural ground. This implies, okay, we have been told that the height of the natural ground of the BM6 has been given, right? It has been given, but we have been told that the formation height, that is the project height of that initial point now, will be 0.6 meter lower than the height of natural ground, which simply means that the height of natural ground on BM6 will now be the height of the project height on BM6. We have been told that the formation height on the initial point was BM6, is 0.6 meter lower than the height of natural ground of that point, which is BM6. So that implies that if we want to get the project height of BM6, we have to take the height of the natural terrain of BM6 minus 0.6 meter. So we have it here, height of natural terrain of natural ground of BM6 minus 0.6 meter, and we had a new project height on BM6 will be 205.4. That means when they will start commencing the road project, what they have gotten as the height of natural ground on BM6, they have to cut 0.6 meter, and when the 0.6 meter is being cut, we are going to have a new height on that point, which is a project height, which is 205.4 meter. So now the formula to calculate the other point, remember that we have a gradient that we want to work on. The formula now to calculate the other project height of the other point now will be the project height of the next point will be the project height of the initial point plus the gradient of that on that segment multiplied by the accumulative distance, isn't it? So we are going to take, if we want to apply that formula, we are going to see that the project height of point A will be the initial project height. The initial project height was the project height we have calculated on BM6 plus 0.01 plus the gradient on that segment. If we go there, we were told that the gradient was under 1.00%. So if we want to convert 1.00%, we are going to have 0.01 multiplied by the distance. If we still go there, we are going to see the distance between BM6 and A is 15.25. So we are going to see 0.01 multiplied by 15.26. If we do all the mathematics, this is what we are going to have. We are going to have 205.552. Same formula, same method. We are going to apply the same procedure, the project height of the initial point plus the gradient of that segment multiplied by the cumulative distances. Now from A to B, we had a distance of 30.5. So we apply it. We have calculated the project height of all the points. You will discover that on point G. On point G now, what are you going to discover on point G? The gradient is not the same. So if you go back to the sketch, you're going to see from F to G, we have another gradient of minus 0.75%. That implies that we have to convert now. We have to multiply this distance from here to here with the distance from F to G with this new gradient. Okay, this is it. And the initial project height now of that point now, since it is the initial project height of that point, it is of that segment. The initial project height of that segment is point F. This is the segment. The initial project height of this segment from here to here is point F. So we actually have two segments. This segment from BM6 to point F, and the initial project height of this segment is on BM6, of course, and the initial project height of this segment from F to G is on point F. Now, the next question now was, we have calculated the height of natural ground, we have calculated the project height, and the next question was to calculate the working height. Of course, if we have our height, if we have observed the height of natural terrain and we have calculated the project height, it's now very easy to calculate the working height. The working height here is given by the formula height of project height of that point minus height of project height of a point minus the height of natural ground of a point. So if you want to calculate the working height on PM6, will be height of project height on PM6 minus height of natural ground on PM6. The formula goes all through. So this is the height of natural ground of some points we have calculated. Now the last question was to realize the longitudinal profile of the natural ground and the lateral profile of the project height. Now, if we look at this sketch, we are going to see this is the longitudinal profile of the natural ground, which has been represented on thick lines, and we have another profile which is the lateral profile of the project height, which has been represented on dotted lines. Now, let's try to see the first point. The first point, we have been told that sorry, let's go back there. Okay, we have been told that, and let's go back to the sketch. Okay, let's see. What was the height? Let's try to locate the height of the natural ground of point A, and the height of natural ground on point A was calculated to be 206.025, and we have been told that the vertical scale will be used. The vertical scale is scale 1:100, and the longitudinal scale is scale 1:1000. That means we are going to use this scale for the height, and we are going to use this scale for the distances to represent the distances. So we have a distance of we have a distance from A, from initial point BM6 to A, which is 15.26. So we have to represent 15.26 with a scale 1:1000. Scale 1:1000 simply means every 1 centimeter you measure on the plan represent 1000 centimeter in the terrain, which simply means again every 1 centimeter you measure on the plan represent 10 meter in the terrain. So we have actually come here, we are graduating our on the x-axis to following the scale. 1 centimeter, we have 1 centimeter, 2 centimeter, 3 centimeter, 4 centimeter, 5 centimeter, 6 centimeter, 7 centimeter, 8 centimeter, 9 centimeter, 10, right up to 16 centimeter. That means since we are working with scale 1:1000, which means every 1 centimeter on the paper represents 10 meter on the terrain. That is, this is 10 meter, 20 meter, 30 meter, 40 meter, 50 meter, and 60, right up to 160 meter. Then the vertical scale was scale 1:100, which simply means every 1 centimeter you measure in the terrain on the plan represent 1 meter in the terrain. So if you want to use 200 as our datum, as we want to take 200 from the Cartesian as our datum or starting point, we have 201, 202, 203, 204, 205, 206, right up to 209, isn't it? Yes. So let's take the first and let's go back to the height of natural ground on point A. Height of natural ground on point A is 206.025. 206.025. So if we want to represent 206, this 205 now, then 206, this is where 206 for 0.025, just slightly above 206. And remember, it's our initial distance, so it is distance 0, 0. So of course, it will be on this axis. If we want to put it, if we want to take a projection between the vertical, we want to take a vertical projection and a horizontal projection. Of course, point BM6 will fall 206. Sorry, that was not PM. That was point A we are talking about. Let's go back to point BM6. What is the height of point BM6? The first point. Let's represent the first point. The first point was 206. Okay, 206. So our point 200 and BM6 will obviously fall here. The distance 0, height 206. So this is 206. This is PM6. Now let's represent now. Let's represent now under point A. Point A, remember the height reading of the height of natural ground on point A was 200 and let's go back and see. Point A was 206.025. That is slightly above 206, 206.025. 206.025 will fall some, this 206 will fall somewhere here, but the distance from BM6 to A was 15 point, yeah, it was 15 point. So this is our 10 meter. Of course, our sense will tell us that, our common sense will tell us if this is 10 meter, half of it will be 15 meters. So this is 15 meter. We have 15 point what? Let's go back to the sketch and see. We had 15.25. So 15.25 falls here, isn't it? This is point A, and this is the height of point A. To get where point A actually falls, we do a vertical projection, and from the distance, and a horizontal projection from the height. Where they intersect, of course, that's where point A will be. Now let's also represent the height of natural ground on point B. And the point B now, what is the distance on point B? Let's go back to the sketch. From point A, from BM6 to point B, we have a distance of 15.25 times 2, isn't it? Yes, which should give us 30 point something. If we do our mathematics, we are going to calculate it now. So if we want to represent under point 2 will obviously for 30 point something. This is where for 30 meter, 30 point. That is a point that's for it falls somewhere here. Now the height. Now we look at the height. We look at the height on point B. On point B, we mark it. Then we take a horizontal projection of the height to point B and the vertical projection from the distance to point B. Where they intersect, we put point B. Same thing is done on point C, point G. Then after when we have done all those, we can now link it with the freehand or with the pencil. With the freehand and the pencil, we can now link the point. We see we have linked point BM6. We have linked it to A, link it to B, link to C, link right up to G. So this is actually how the terrain looks like. This is actually how the terrain looks like. So here we have realized the profile of the natural ground. Now we can still go now and apply the same principles. Apply the same principle to represent the profile of the project height. When we apply the same principles, then we link the point. We are going to see. We are going to represent the profile of the profile of the project. Yes, the longitudinal profile of the project. We tick dotted lines. This is it. This is it. And now, if we look again here, you're going to see fill. You're going to see cut. When the longitudinal profile of the natural ground lies below, the profile, the project profile, and then we know we are going to fill. Of course, for us to realize this project, we have to fill the ground. We have to do some filling of groundwork here so that we can attain this our intended or project profile. Then here, if we want to, this is the profile. This is the profile of the natural ground which lies above the project profile. So if we want to realize this project here, of course, we are going to cut. We are going to cut to reach the point of reach the project profile. Okay, thank you very much. Hope you grab the concept.